What happens if you combine two u01? Okay, before we do that, let me say that the concept of IID is obviously the same here also. What does IID always mean? Independent and identically distributed. So this exact same thing that we had for discrete happens here, but this is valid here also. So IID same as in discrete, right? So let x and y be u01, two continuous IID. So what is a joint PDF going to look like? Where is the joint PDF going to have its support? If I want to combine them. So these are two random number generators independently spinning away, and this gives you a number x, this gives you a number y. We take them together and plot them on the plane. So what's going to be the omega xy is going to be the unit square 0 1. You can think of it as something like the 0 1. I'm not sure this notation is right. We can just put it right. Maybe we should just simply, or it's maybe better to write it like this. Ignore this. Write it like this. So remember, right, when you plot these things, you are always plotting values taken by x along the x axis and always plotting the values taken by y along the y axis, and any point here is the x coordinate is the value taken by x and the y coordinate is the value taken by y. That's all. That's a convention we are following uniformly everywhere. And it's obviously not just true of xy. I could have zw. So whatever random variable I put first will always be horizontal axis. Whatever random variable comes second will always be vertical. Convention, right? Don't need to change. So here of course they are IID, so it doesn't matter, but anyhow we have to keep the convention xy. So this is omega xy, this the unit square. What is fxy by construction? Obviously unity in the square. One into 1 is 1, 1 into 0 is 0. The simplest multiplication anybody can do. So for xy in omega x, this omega xy and 0 otherwise. So you can say instead of saying, well, I start with this and I form this, it need not always be said. You can just simply start directly with this. Let x and y be two random variables defined on the unit square and such that the density function is constant. Then obviously the whole thing holds. You don't have to say, you don't have to start with this all the time. How would I combine two Gaussian PDFs? Just to say this was kind of a, okay, it's a very important example, no, because U01 it turns out is our basic random number generator, so we have to understand it like everything, all the things we can do with it we need to know, right? We will do a lot more things with it, but let's move away from U01 and look at Gaussian. Supposing we have two, both 0 mean for simplicity, but let's say different variances, and let's say they are, we know that they are independent to begin with, then how are we going to form the joint PDF? So this is example, okay. Then example again. Let x be some Gaussian sigma 1 squared. I need to have different variances, so I will put 1 and 2. Y is another Gaussian sigma 2 squared independent. Now I cannot call them IID because I am not saying that sigma 1 is equal to sigma 2, so obviously they are not in general IID. If sigma 1 equals sigma 2, then they become IID. Remember, IID is not only independent, also identically distributed, means I have to have the same PDF or PMF, right. Okay, but I am just saying there are two independent random variables, that obviously means they are coming from two independent sources, two independent experiments. So if you now want to combine them, so in this case what is omega x and omega y, both of them are the entire real line. So when you combine them, the omega xy will be the whole plane. Is the entire xy plane, which is to say that any point in that plane can occur in the joint experiment, which you where you consider both observations. Okay, here, okay, one I should mark this also. This is 1, right? Okay, that's the first part. The second part is in a way the easy part, which doesn't require any mathematics. I mean, it doesn't require any calculations. What about fxy? When you multiply the two Gaussians, what happens? Well, of course you get this 1 by the square root of 2 pi will give you this. So it will become 1 by sigma, wait a minute, sigma 1, sigma 2, right. Now the interesting part is just algebraically that when you take the product of two exponentials, you can add the arguments. That is a crucial thing here in terms of simplifying this. So later on we will do a lot of manipulations with this. So in this case, what does the manipulation tell you? It is 1 minus 1 by x squared by 2 sigma 1 squared, and you can put one more bracket out here because this is the common way in which this is written. Of course I can pull out the half also. If I pull out the half, I get minus half of x squared by sigma 1 squared plus y squared by sigma 2 squared, and I need one more bracket to round it off, otherwise mathematically it's incomplete, so we will put that. So this is for all xy. So this is an example of a joint PDF which is asymptotically decaying to 0 as you move away from the origin. If you have non-zero means, it is exactly the same thing except there is a little more algebra, right. You would get that is an m parameter, x minus m, y minus whatever, m1 m2, but the principle is the same. So what happens in these Gaussian cases is that you have this constant term here, you have x of minus, and then that half is usually pulled out, and you get what does this look like? This is going to be an interesting quadratic in x and y. If they are independent, the quadratic will not have an xy term. It will just have x squared by some constant plus y squared by another constant, and it will also have, supposing the means are also there, it will also have some x by some constant. You can always complete the square, right. If you have terms like x squared, y squared, x and y without the xy, you can always write it as a square on x and a square on y just by completing the square. All of you can complete squares hopefully, right, you have not forgotten that. If you have an xy, then it turns out is fundamentally different, right. That is again something we are going to study later on, right. That turns out to be a very interesting case of joint Gaussian where x and y are not independent, they are dependent. We will come to that maybe in a homework problem for right now, but later on we will look at it in more detail. Okay. Anyway, so in the independent Gaussian case, you should easily be able to tell it, look at it and say. So instead of x I can have x minus m1 whole squared, instead of this y I can have y minus m2 whole squared, and you should be able to expand that out, and you may get one more constant which is independent of x and y. You can pull that out and multiply it with this. All of those things are obviously possible. If I want to combine two exponentials, which is another very practically significant one last example we will do. Supposing I say let x be some exponential of lambda 1. This means an exponential distribution with parameter lambda 1, right, and y is exponential with parameter lambda 2. This also is a case where the arguments with exponentials will combine. So what happens here, the omega xy is only the first quadrant now, because x and y are both so called non-negative random variables. When they do not take negative values, you call them non-negative. So omega xy is the first quadrant. So of course I should say they are independent, right? And what is fxy? Lambda 1 lambda 2 x of what? Minus lambda 1x plus lambda 2y. For xy, you say it like this: x comma y greater than equal to 0. That is also obviously important. It is understood that when either one x or y is negative, the joint PDF is 0. So again here, by looking at this, if somebody starts off with this, you should immediately recognize this as right, x and y being independently exponential, because immediately you have product. And this is going to be always a correct normalizing factor no matter what. If it is not, well, then I mean you might have to tweak it to make it the correct normalizing factor, but in some books or papers you right, not more in some poorly written paper than a book, hopefully, right, you might find some authors working with some either a wrong normalizing factor or just some k, whatever. You can always find out the correct value for that. So before I move on, supposing here if they are IID, this sigma 1 equal to sigma 2, then you get further simplification here, that is obvious, isn't it? The denominator will be common and it will just be x squared plus y squared by 2 sigma squared. Just that also possibility you should be alert to. That is the simplest possible case. Okay, so this I think should be sufficient for now to illustrate independent continuous random variables, right. The important factorization I think we have explained very clearly. Does anyone have any questions or anything regarding this? So before that, let me also say that most interesting cases of two random variables, you do not want them to be independent, you want them to be dependent. If they are just independent, in fact it turns out that the joint PDF is in some sense a redundant statement. You can as well only limit yourselves to the marginals. So most interesting of x joint right, x and y are is the dependent case. This is exactly as in discrete, right. So how do you straightaway can you tell if the necessary condition for omega xy is not satisfied? What is the necessary condition of omega xy? It has to be regular with respect to the x and y axis. If that is not satisfied, then automatically you know that x and y are dependent. For example, in the trinomial PMF, we could straightaway tell, because x and y were limited to some triangular region. So whenever something like that happens, I mean it may not be the full triangle, but at least the points all lay inside a triangle and not the non-zero probability points were not outside that triangle. Likewise here, if your x and y jointly are in a circle or in any triangle or any such thing, clearly it cannot be independent, they have to be dependent.